Hey, what's up, guys? Okay, so in this video that I want to remake some video discuss about the bounding the BQP. Basically, is the notion of like efficiently simple if the decision problem that one can efficiently solve using the quantum computer. Okay, so let me just quickly recall some basic fact. But basically, the concept of this in the next video is just to prove the upper bound of BQP. Okay, so recall that the language L is in BQP. If there is a uniform family, uniform family. Basically, it's so you need to like the requirement is that you need to construct this uniform family in polynomial time. Uniform family of quantum circuit. Okay, let's call it Cn, and such that for input, let's say your input is x1 to the n. Okay, such that if x belongs to L, then your quantum circuit need to output the successful probability greater than 2 divided by 3 or 2/3. Okay, so greater than equal. So your Cn need to accept or output 1 with probability greater than 2 divided by 3. So the randomness comes from the quantum itself. If you use the quantum gates or use the measurement, there will be the internal randomness. If x not belongs L, then probability of C and accept it is strictly greater than less than 1 divided by 3, 1/3. Okay, so this looks very similar as a BPP. Okay, if you use the classical BPP, then you replace this probability to be the random bit, random flip that you assign to this your Turing machine. Okay, so there's some technical detail. Okay, some detail is that right, so your starting point usually will be the 0 to the q to the n, where q to the n is poly. Okay, so it's polynomial in n. It's polynomial in n. Okay, and the gate, right? The gate you can only use in principle is you can only use the universal gate set. Okay, so there are very small sets of gates that you can the only case that you can use. Okay, so there are some comma gates, which is Hadamard gate, and XYZ, and also the phase gate. So the phase gates look like this, and also CNAR gate. Okay, so CNAR gate basically map XY to the XX control Y. Okay, or X bit. This is n, the big sum. Okay, so 1 plus 1 is 0. 0 plus 1, 1 plus 0 are both 1, and 0 plus 0 is 0. And also the Toffoli gate. So let's go CC not gate. Okay, or T gate. Basically, it's X, Y, Z goes to X, Y, Z. This. Okay, so it's the bit sum. It's XOR. Okay, should be XOR. Okay. And okay, and there is an idea called the universal gate set. Gate set. Okay, so the compare is that in the classical, right? In the classical like circuit or classical Boolean circuit, one can prove that NAND and the NOR are universal. So basically, you can show that the AND gate or gates or whatever gates can be constructed by NAND and NOR gate, and then you can prove can see my see my other videos. Okay, I will post the link below. Okay, so see my other videos. Okay, and the fact that there is a universal gate set, also the same thing. In the quantum is basically usually we can use the simple ones, the Toffoli gates and the Hadamard gates, or the Sina gate, H gate, and there's a pi divided by 8 gate. Okay, so pi divided by 8 means that you can do 1, 0, 0 exponential I pi divided by 8. I think 2 pi divided by 8. Yeah. So this rotation gate should be good enough. Okay, but in the proof that one can always use this gate set. Okay. And there's a theorem called Solovay-Kitaev. So I can make a video to prove this. I think this is not so trivial, but one can show this. So if G is universal and closed under inversion, so G is universal and closed under the inversion, under the inverse. So as a group, or sorry, you define a G is universal. Okay. So first one and close under the inverse as a group. Then as for then arbitrary epsilon, any unitary operator U. Okay. Can be approximately, so it can be approximate. Can be approximately using polynomial, polylog 1 over epsilon gates in G. Okay, so yeah, so basically this is the theorem called Solovay-Kitaev. Okay, so yeah, so that means that now we can use our BQP, right? You imagine that our BQP can start with all this 0 to n or poly n of lambda and only apply the poly sides, only apply the polynomial number of gate. Let's say this is m, which is polynomial in n, and the only gate we can apply is Hadamard gates and the CC naught, only the Toffoli gates and these two gates. Okay, so one can you can solve if you can. The problem in the BQP basically means that there's a circuit such that this quantum circuit can decide where x belongs to L or not. Okay, and so yeah, this is the introduction. So now we are okay. Okay, and next video that I want to talk about relationship to other complexity classes. Okay, so our goal will to prove the following. So B is a subset of BPP, is subset of BQP, and also PP and the P space, and the XP. Okay, so see you guys in the next videos.